Swati Verma, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, CSVTU Bhilai. I welcome you all to the course of Industrial Automation and Drive. Today we will begin with our 13th lecture with the title PLC Programming Third. Till now we have seen the binary concept, the PLC programming rules, the PLC programming for the basic logic gates like AND, OR and the NOT gate, and in today's class we will start with the PLC programming for the universal gates NAND and NOR. So let's start with the NAND function. Here in the figure you can see the logic symbol of the NAND gate. Okay. So basically by adding a NOT gate function with the AND function we can create a NAND function. Okay. You can see the NAND truth table here with two inputs A and B and output Y. Here you can see when the input is 0 0, output is 1. When the inputs are 0 1 1 0, output is 1. But when all the inputs are high, output is 0. So now we will implement this NAND function by using a ladder programming. So basically we can design the NAND function by using the two switches in the form normally closed switches in a parallel form. Okay, let's consider a case 1 in which A is 0, B is 0. Okay, so you can see there are two inputs we have connected in switches, input switches we have connected in parallel. Okay, with the input addressing I0, I colon 0 slash 0, I colon 0 slash 1, and an output is connected at the right ladder with the addressing O0 slash 0. Okay, so when A is 0, B is 0, it means there is low output and the switches will remain in their state, means it will remain in their closed condition. So we will get a high output in this case. In the second case, when the input is 0 and B is 1, so the first switch A will remain in its normally closed condition, but since we are giving one input to the B switch, it will change its state from normally closed to normally open. But here in this case also we will get the output, high output through the rung 1 or through the switch A. So in this case we will get the high output. In the third case with A1 and B0, the first switch A will change its state from normally closed to normally open, and since the B is 0, the second switch will remain in its normally closed condition. So we will get power through the second switch, through the first switch, and we will get a high output in this case. Now the last case in which both the inputs are 1, so both the input switches will change their state from normally closed to normally open, and through both the path we will not get any power flow and our output will be 0. Okay, so by this you can clearly see that we can implement all the 4 cases of the NAND connection by simply connecting two normally closed switches in a parallel condition. Okay, similarly now comes the NOR gate. So what is a NOR gate? We have discussed already. The OR gate plus a NOR gate will become a NOR gate. Okay, you can clearly see the symbol of the two input NOR gate and the truth table of it. So when both the inputs are 0, output will be 1, while rest of the 3 cases for 0 1, 1 0, 1 1, output will be 0. Means we will get a high output when both the inputs are 0, and we will get a 0 or the low output in any of the remaining cases for 0 1, 1 0 and 1 1. So how we will implement the NOR function in a logic diagram? Now we will see. So for the case 1, when A is 0, B is 0, for implement the NOR function, we have connected two normally closed switches in a series connection. Like you can see here, we have connected two switches with the addressing I colon 0 slash 0 slash 1 in a series with the output. Okay, so when A is 0, B is 0, they will remain in their normally closed case and we will get a high output. Okay, but when the second case, when A is 0, B is 1, A will remain in its normally closed condition, but since B is getting 1, it will change its state from normally closed to normally open. There will be no path for the power flow and we will get a 0 output in this case. Similarly, in the third case, when A is 1, B is 0, first switch will change its state from normally closed to normally open, and B will remain in its normally closed condition. But in this case also, since both are connected in series, we will not get any power at the output, so output will be 0 or low. Now the fourth case, when both the inputs are high, both the switches will change their state from normally closed to normally open. The path will get open, and since no power flow to the output, we will get a 0 case. So here we have considered all the 4 cases of the NOR function. Okay, so it's clear that we can simply implement the NOR function by connecting two normally closed gates in a series connection. Okay, now comes the PLC programming for the spatial gate. First, the XOR gate. So here you can see the truth table and the logical symbol of the XOR gate. So while you see the truth table, the output will be 0 when the inputs are same, means 0 0 1 1, and when the inputs are different like 0 1 1 0, output will be high. So here you can see that how we can create or implement this XOR function to the ladder program. Okay, so here you can see that we have connected, in the figure you can see there are the 4 switches, but since the inputs are 2 only, A and B, we are only using the 2 addressing. So here you can see the switches are 4, but we have used only 2 addressing mode to address that switches. So you can see in the first rung, two switches are connected. First switch with the addressing I0 I:0/0, which is in normally open K condition, and the second input and the second switch which is in normally closed condition with the addressing I0 I:0/1. While in the second rung we have used two switches with the same addressing I:0/0 and I:0/1. So but in the first we are using one normally closed, normally open. In the second, we have used the first switch in the normally closed case, and the second switch is normally open condition. So when the input is 0, output is 0, both the switches will remain in their same state and we will get a 0 output. But in the second case, when A is 0 and B is 1, so the first switch in first will remain in its state, okay, but the second switch B, which is in the first rung, which is in normally closed condition, will become open, and the open switch which is in the rung 2 will get closed. Okay, so in the first rung will get open, but the second we will get the power through the second rung. Since both A and B are closed condition in the second rung, we will get a high output. Okay, now next the third case with when A is 1 and B is 0. So now the first switch, which is in normally open case will become normally closed, and the second rung in which it is the same addressing mode which is normally closed will become normally open. Okay, while the next switch will remain in its state. So in the first rung we will get two normally closed case, we will get a complete path for the power transfer and we will get a high output in this case. While in the fourth case, when A is 1, B is 1, all the 4 switches will change its state. Okay, so in the first case, the first switch will become normally open to normally closed. In the second rung, it will become normally closed to normally open, while the second switch in first rung will become normally closed to normally open, and in the second rung, it will become normally open to normally closed. So while we will not get any power through any of this path, okay, any of this rung, and we will get a 0 output. So now we can, it is clear that we can implement the XOR function by using 4 switches, but with the different cases. One is in one rung, first is in open and second is in closed case, but we are using only 2 addressing mode to address that 4 switches. So 2 of the switches have the same addressing mode. Now the XNOR function. In the figure, you can clearly see the logic symbol of XNOR and the truth table. So in the XNOR we know the output will be high when both the inputs are same, means 0 0 1 1, and the output will be low when the inputs are different, means 0 1 and 1 0 case. So here we can implement the XNOR function. Similarly, here we are using the 4 switches, but we are using the 2 addressing mode only since we have 2 inputs. Okay, so in the first case we have connected I colon 0 slash 1 in the open case, but in the second rung we have used the same addressing for the second normally closed switch. Or similarly in the first rung we have used a second switch with normally open switch with the addressing I0 colon 1, and in the second rung we have used the same addressing for the same address to address the in normally closed switch, which will we have the same addressing mode like the first rung. Okay, so in this case when A is 0, B is 0, so the first rung will become open, second rung will get closed and will remain in their state and we will get a high output. In the second case when A is 0, B is 1, so the first input or the /0/0 addressing mode switch will remain in their state, while the second switch with the addressing I colon 0/1 will change their state. So in the first rung also, second rung also, we will not get any power and we will get a 0 output. In the third case similarly, the first switch will get normally open to normally closed. In the second rung it will get normally closed to normally open, while the second switch will remain in its state since B is 0 and we will not get any output power. Why not the fourth case when A is 1, B is 1, all the 4 switches will change their state. In the first rung will become normally open to normally closed. The second rung will become, in the second rung it will become normally closed to normally open mode. Then now the second switch in the first rung will become normally open to normally closed, and the second rung it will become the second switch will become normally closed to normally open. So we'll get a high power through the first rung and the output will be high. Now let's take some example of how we can convert a Boolean expression into the ladder program. So now consider the first expression which read A not B, A multiplied by B plus C multiplied by D plus E multiplied by F plus G bar equal to the output Y. So to implement this algebra or this Boolean expression into the ladder diagram, just keep it this in mind what we have learned in our binary concept, that to connect any two switches in the multiplied or in the AND function, we have to connect the switches in series. Okay, but to connect but to implement the OR gate or to plus, we have to connect this two switches in the parallel connection. Similarly, how to implement the NOT or the complement function. So here we can see in the our given expression G bar. So here is how we can implement. If we can simply use a normally closed switch to implement the gate G bar, so that when we give the 0, it will remain in its state and we will get a high output, but when you will give 1, it will change its state, it will become open and you will get a 0 output. So that's how we can implement the complement function. So in the figure you can clearly see, first implement A not B means A and B. We have connected A and B switches in series form. Now C multiplied by D, we have connected C and D switches in the series form. Next, to implement the F plus G bar, we have connected the F and the G switch in the parallel form, but here we have used the G in the normally closed condition to implement the complement of G. Okay, and to AND it with the E, we have connected E in the series with the parallel of F and G. So since all of these forms, this Boolean multiplied functions are connected by plus, we have connected all this A, B, E, D, E, F, G form in the parallel connection to get the output in the Y. Okay, clear. So next is the Boolean expression. Okay, P plus Q bar plus R multiplied with S plus T multiplied by U bar multiplied by V, this is the one function, then plus W plus X into Y. So now break it into forms. First we will design in the brackets. Okay, so P plus Q bar plus R. So here we have connected the P, Q bar means the normally closed switch is used for the Q, and the R in the parallel connection. Similarly, to implement the S plus T, we have connected S and the T switch in the parallel form. Okay, now all these functions are connected in series, means P plus Q bar R, S plus T bar is connected in series with U and V, where U for U we have connected normally close, we have used a normally closed switch. Okay, now this complete is connected in with an OR function with W plus X into Y. For this we have connected W plus X in a parallel with series with the Y function, and all of this is connected in the parallel with above expression P plus Q bar R, X plus T, U bar into V to get the desired output using output switch with that which we have indicated by the Z. Okay, so this is how we can implement a Boolean expression. Now next, here A dot B plus C dot D multiplied by with or and with E dot Z plus F bar equal to Z. Okay, so how we can here you can see we have 7 inputs, but Z is used twice. Z is in the output also and Z is in the input also. So let's consider A dot B. So we have connected A and B switch in series in parallel with C and D switch. Okay, similarly to implement Z plus F bar, we have connected Z and F bar, normally closed switch for F, we have connected them in parallel in series with the E to get the AND operation, and in series with the A cross B and C plus D form to get a complete AND connection, and then we have get an output. But you have remembered that in the previous class I have addressed all the programming rules. Okay, so here how we can address both, since the Z is switch is used in both the input and the output, but you have to remember that the output Z address can be used as a for the input switch addressing, but we can't address the output like any input switch. Okay, so in the output we have addressed the output as a O colon 0 slash 0. So in the input side, input switch, we have addressed same like the output O colon 0 slash 0. Okay, so keep this in mind. This is an important point in this example. Okay, now next, L plus M bar plus N plus Q into R complemented, complete complemented, is multiplied by R equal to Z. So now break into two form. So how you can implement L plus M bar plus N? By connecting L, M and N switches in parallel. In for M, since it is complemented, we have used the normally closed switch. Okay, and how we can implement Q multiplied by R? We have connected in the series Q and R switches in the series and in parallel with the L plus M bar plus N to get an OR operation. Okay, now next, multiplied, since the complement is stated, so here we have used a binary bit from the data file, which you remember I have discussed in the data files. Okay, while the addressing, input addressing is B3 colon 0 slash 0. Okay, and in the second run we have connected this binary bit in the normally closed case, means we have complemented it, so that if B3 is low in the first rung, it will get high in the second rung, and if the B3 is high in the first rung, it will get low in the second rung. Okay, since we have used a normally closed switch in the second rung. Got it? Okay, so here we have used the B3 colon 0 in the first rung, and in the second rung we have complemented it. Similarly, multiplied with R, we have connected the R switch in series with the R to get the final output, our Z. Okay, so you can also note that here in the input expression we have used R 2 times in the input. So we have given the same addressing to both the R switch, because we can give same input addressing to number of our inputs. It is possible. Okay, you can use the same input addressing to address the different or many number of input switches. Okay, so clearly you can see in the first rung and in the second rung the input addressing of R switch I colon 0 slash 4 in first rung, and it's similar to the I colon 0 slash 4 in the second rung. Okay, so this type of connection in which we have break the first form into any binary form is called as the interlocking. Okay, it is very important. It is commonly used in the industry process. Now let's understand this interlocking with another example. Okay, suppose we have three toggle switches, SW1, SW2 and SW3, and 3 digital output DI1, DI2 and DI3. So now what the case is, if any one switch is on output DI1 will be high only. And case 2, if any two switches on, only the output Di2 will be high. Case 3, when all the 3 switches are on, then only the output Di3 will be high. Please focus the word only, this is very important. So let's programming with the third case. When all the switches are on, means we have to connect them in using the AND logic and in the series. So here you can see in the first rung we are using the 3 switches. Okay, so in the first case all the 3 switches are connected in series to get the Di3 on. In the second you can see we are using the 3 series in the OR, so any one is out, output will be high. In the third rung you can see we have connected 2 switches in series, means if any of the 2 switch will high, the output will be high. In the basic condition you will think that oh, it is correct, but no, in the case we have focused on the word only. So just consider this ladder diagram. If any two switches are on, for example switch 1 and switch 2, what will happen? The Di1 input will be on, will get high, and Di2 output will be Di2 output will be high. Means both the switch output will be get high. But according to our condition, if two switches are on, only Di2 output should be high. Okay, so in that case we have to provide interlocking. Got it? So clear, you can see in the figure, this is the correct ladder diagram for that case with the interlocking condition. Okay, we have only 3 addressing modes. Okay, so in all the parts we have used 3 addressing, we have repeated that addressing modes to address in the input. Okay, when the first one is high, all the 3 is high, output will be high, D0 will be high. When any one will be high, D1 will be high, and in the third, if any 2 switches will be high, then only the output D2 will be high. So now our condition is met by connecting the switches in this form using the interlocking condition. Okay. Okay. Now let's talk about the latch circuit and the logic. Here in the figure you can see the 2-coil mechanical latching relay. Okay, in the figure. So now what's the latching relays? Basically the latching relays are designed to hold the relay closed after power has been removed from the coil. The latching relays are basically used where it is necessary for the contact to stay open or to stay closed even though the coil is energized only for a moment. Okay, so the latch coil is momentarily energized to set the latch and to hold the relay in the latch condition throughout. But next, what is the unlatch or the release coil? This unlatch or the release coil is momentarily energized to disengage the mechanical latch and to return the relay to the unlatched condition. Here you can see we have the symbol for the latch, output latch is shown by the L, and in the output unlatch is shown by the U. Okay, here you can see the input. Okay, and here you can clearly see the ladder program for this latch and unlatch condition. Okay, we have used 2 switches with the addressing I:1/0, I:1/1. 1/0 is for the latch and the /1/1 is for the unlatch. Both are connected to the same output with the addressing 0:2/5, means the output is connected to the 5th slot. Okay, now here when the input I/1/0 is high, output will go high, but even when the I/0 or the first switch will become low or our latch switch will become low, output will remain high. That is the condition. Okay, or now the output will keep remain high but will get low only and only when input 1 or the unlatched switch will become high. Okay, so which means when the input is high, our output will go high in that condition. But even if you remove the input or even if you make the low output to the first input, output will remain high. Means Not changing the input status of the first switch will not change the running status of your output. You can only stop the output, or the output will become low only when you activate or make the unlatch switch high. Okay. Next is the basic start stop concept, which are generally used in the industry or automation process. Previously we have understand the ladder logic, how in this we have used the toggle buttons for all the input switches, but you have seen that in the industry we generally use the push buttons. You have seen in the motors also the green and red switches, which are used to start any process, the machine or motor, for enhanced safety, for the precise control, and also for the better integration with the automation systems. Okay, but the question comes, why the push buttons are used and how it provides safety and precise control in the industries. How we are not we are not using the toggle switches which we generally use in our home appliances or in the home. So the question, the answer lies in the working of the toggle switch and the your stop and start switch. Okay, so just now let's take a how the toggle button works. When you turn it on, when you toggle it on, it activates the output, and when you turn it off, it will deactivate the output. Okay, but when I use the start and stop or the red and green buttons to control the motor, pressing the green button will turn the motor on and it will get released, but it will keep the motor on. Then you will keep pressing the green button, it will not keep your motor off until you don't press the red button to stop the motor. Okay, means we have different switches to start and stop, but in the toggle switch we can simply turn it on and off, which to make the output on and off. But in the red and green push buttons, or the buttons, we simply when you press the green button, the motor will on, but if you release it, it will not make the motor off. Okay, and if you want the motor off, you have to press the red button. Okay, just think the scenario, what happens if the power goes off in both the cases, in the toggle button case and in the start and the stop button case. Okay, so in the both conditions, when the power will be off, okay, the motor will turn off. Okay, in both the cases motor will turn off. But if consider if the power comes back after 5 minutes, the motor in the toggle switch will turn automatically on. Okay, you don't need to press it on. Okay, means just consider a case of yours, a fan at home, or the refrigerator at your home. When the power goes off, it get off, but when the power comes, automatically it will turn on. Okay, but but this is not in the case in the push and the in the red and the green buttons, in the start and the stop buttons. If the power goes out, it will turn off, but when the power comes back, okay, it will not automatically turns on. Okay, means to turn the motor on, you have to press it on again. So in the toggle switch, when the power comes back, it automatically turns on again and leaves with you no control. Okay, but in the push button case, in the start stop concept, when the power comes, the motor will not turn automatically. It will give you control when you have to, or when you need to turn it on again. This means we have control over when to turn it on. Okay, in the press buttons. So if we consider the power outage as a fault condition, so after the fault, using the push buttons will give you control over when to turn the entire system back. Okay, this is why push buttons are used in industry instead of toggle switches. Okay, so where the controlling is important, we use the push buttons. Okay, so now how we can implement the push buttons or the start stop concept through the ladder programming. You will see in the figure, you can see we have used two buttons. First the green button to start, or you can say the start button with a normally open switch with the addressing I colon O/0, and the red button with the normally closed switch with the addressing I colon 0/1. Okay, and we have connected a binary bit at the first in the first string as an output with an addressing b colon 3 b3 colon 0 slash 0, and same addressing we have used in the switch which is connected in parallel with our start button. Okay, and same binary bit is connected in series with the output or with our motor in the second rung, as you can clearly see in the diagram. Now consider a case when you press the start button or you press the green button. So now when you press the green button, the motor, so here you can see the normally open switch, green button will change its state to normally closed, and you will get a high output, or B3 will be high. So so when the B3 will be high, the inputs with the same addressing like the B3 will also get high. So the B3 switch connected in parallel with the green button will be also get high, and connected with the output will be also get high. So we'll get a high high B3 and your motor will turn on. So now when you again press the B3 button or will change its state, it will there will be no effect. Your B3 and motor will remain on. Okay, so this condition is called as a latching condition. Okay, so now when you will stop the motor, okay, so for this you have to press the red button or the stop button. Okay, so when you give 1 to the stop button, since it is initially in the normally closed switch, it will become normally open, so there will be no power to the B3 in through the first rung. It will get 0, and through the second rung your output will get 0 and your motor will turn off. So by this is through this ladder program, or by connecting this the inputs by using the two switches and using a binary concept or the binary bit, we can implement the basic start and stop concept using the ladder diagram. So that's all for this lecture. In this lecture we have covered the PLC programming for the universal gate, the NAND gate, NOR gate, and the special gates like the XOR and XNOR. We've also learned how to convert the Boolean algebra into a ladder programming. We've also learned the concept of interlocking and the latching operation, and the basic start and stop concept and how to implement using a ladder logic. Okay, that's all for today. In the next session we will explore the PLC timer programming, and the Rahul Baghel sir will continue from the next class. Thank you. Happy learning.